Hello, we are Group 3. This is our presentation for the project titled Multi-Class Arrhythmia Classification using 12-lead ECG signals. This is our outline that we will follow throughout this presentation. Arrhythmia means abnormal rhythm. In medical science, arrhythmia refers to the abnormal rhythm of one's heart. This can be caused by cardiac attack, smoking, and many other problems. This is incurable and have severe death risk. ECG refers to the graphical depiction of time-varying voltage of cardiac cycle. In standard ECG, 12 leads are used. Among them, lead 2 is most prominent. The main objective of our project is to automatically identify arrhythmias from 12-lead ECG recordings and specifically classify them according to the 8 classes of arrhythmias. This task is very important as over 31% of the death in the world is caused by cardiovascular disease, among which over 80% of the sudden cardiac deaths are closely related to cardiac arrhythmias. So we want to detect cardiac abnormalities specifically and automatically in real time to ensure faster assistance when necessary, which will help us save millions of lives.
Let's talk about the dataset. We chose a well-known and relatively new dataset, the China Physiological Signal Challenge 2018, which provides parallel ECG records suitable for multi-lead ECG analysis. There are 6877 ECG records collected from 11 hospitals, sampled at 500 Hz, consisting of 9 classes of arrhythmia labelings. There are many existing models proposed by authors on this dataset. We chose one of those existing methods as our baseline model, named Multi-Lead Branch Fusion Network, abbreviated as MLBF-NET. We chose this as our baseline as to our knowledge this is the latest model that outperforms all existing systems of the art models to classify the 8 different arrhythmias. In their case, the total number of model parameters are only about 0.42 million. The branch net includes one-dimensional convolutional blocks, bidirectional GRU blocks, and attention blocks. After extracting the features from each ECG lead individually, they concatenated those features and applied attention to the concatenated features. In the pre-processing part, they downsampled the signal from 500 Hz to 250 Hz to speed up the process. As mentioned earlier, the ECG records have different lengths, but for the CNN classification models need input of equal length. Hence, they use geopadding to equalize all the samples to 60 seconds. In our pre-processing, we also perform the same downsampling method, but to equalize the ECG samples, we have applied a different approach. In the dataset, the minimum length of ECG signal is 6 seconds, so we use a 6-second window with no overlapping to equalize the ECG samples for the input of our model. This process also works as a data augmentation method. It will provide at least one or more than one ECG samples with the same sampling level as the original ECG record. And by doing so, we avoided the false recognition of smaller ECG data samples which might have been trained by the model for zero padding. Now we can see the ECG signals of barrel leads. Normally, a cardiologist looks for the duration and amplitude of QRS complex, the RR interval, the PR interval, the QT interval, ST elevation and depression, the presence or inversion of P wave to diagnose different classes of arrhythmia. Our model also needs to obtain an inherent ECG pattern to classify the classes from many features. So we try to implement the fast Fourier transform or FFT in the frequency domain and the continuous wavelet transform or the CWT pattern of the ECG signal to classify the arrhythmias.
Here, this is our proposed feature, where we adopted the FFT method to extract frequency domain features called as time multiplexed FFT feature, or shortly TMFFT, which is modified by us. And for each 6-second 12-lead ECG sample, we extracted TMFFT feature. Firstly, we divided the sample into some time frames with the duration of 0.6 seconds each. Then each time frame is converted into the frequency domain by applying FFT. As a result, we have some successive time frames where each time frame includes the Fourier transform feature of that time frame. Here, in our case, the calculation of the total number of data samples per time frame and the total number of time frames per ECG record is shown. This TMFFT feature extraction is like short-time Fourier transform or STFT. After obtaining the TMFFT feature from each ECG lead, we have concatenated the features from all leads, which is converted into a 2D feature matrix, and then it is fed into a 2D CNN-based architecture. This is our total classification module. This part is for the TM-A50 feature extraction process, where the discussed time frames, A50 transformed version of each time frame, and the concatenated 2D feature matrix obtained from each 12-lead ECG record are shown visually. Then, this is our 2D CNN-based architecture to extract the deep features from the 2D TM-A50 feature matrix, where two types of CNN kernel are used. The first one is to extract deep features from the frequency domain of each time frame. Here, the time frame dimension is unaffected. And the second one is to extract deep features from the multiplex time frames. After being done with extracting the pattern of ECG signal in frequency domain, now it is time to extract features in time domain also. Because in many signal processing domains, it is well proved that together both frequency and time domain features give more extensive information. To extract the temporal informative features, firstly, we have applied 1D CNN-based architecture for each lead ECG signal. The block diagram for 1D CNN model for each lead is here. After extracting the individual temporal features from each lead of the ECG signal, the features are concatenated for all the leads. And then, to obtain the inherent patterns for the relationship within the ECG leads, a 2D CNN-based model is applied to concatenated temporal features from each lead. Finally, after extracting the deep features from both time and frequency domain individually by using two different types of CNN architecture, both of the models is ensembled to classify the ECG signal with a better inherent pattern.
In this table, we have summarized the performance of the MLBF nets and performance of different models that we have implemented. We can see, though in paper MLBF published F1 score of 85.2%, reproduced model of the MLBF net performs about 75%. However, back to performance of our different approaches. CWT-based classifier performed poorly, which is about 19.87%. Full FFT-based classifier score is about 41%. These results made us to think about a feature that will be lightweight and has both time and frequency information. So when we defined DMFFT feature and designed a simple architecture for classification, we get almost 70% F1 score. This depicts DMFFT is a strong feature that has enough information for classification. As part of exploring, we assembled two architecture that has been discussed in proposed method section. Finally, we can see ensemble network outperform implemented MLBF net. Here is the confusion matrix of the classifier, which shows model is quite confident, which helps to avoid false positive case except fourth class where it has value below 0.6. Table shows the class-wise F1 score of MLBF net and proposed method. MLBF net data are taken from the original article, though we already stated that when we reproduced the MLBF net, we got inferior performance than the paper. So in terms of reproduced MLBF net, our proposed classifier outperforms the MLBF net.
I am describing the cost sheet to implement this project. To implement this project, we need two components. Firstly, we need an ECG machine to collect ECG raw data. That will cost around $700. Secondly, we need a computer with a high-end GPU. We need the high-end GPU to train the dataset, to train the machine, deep learning model we have used. That will cost around, if you use Google Cloud Service, that will cost around $300 per month. So overall, we can say we need minimum $2,000 per month to implement this project.
We are at the very end of our presentation. To conclude, we have explored many and reproduced some state-of-the-art for arrhythmia classification. We have tried both time and frequency information for classification purpose. We assembled two separate models to make classifier more confident to avoid false positive. Our proposed model outperforms reproduced model of MLBF architecture. To talk about future aspect, DMFFT is a novel feature and need to develop architecture that can extract maximum information from the feature for classification purpose. We are also thinking of applying and comparing this both time and frequency information included lightweight feature instead of CWT FFT feature in other classification application.